Okay, those of you getting ready for the AP Physics C exam, this is a review of kinematics, or basically how things move in a circle. When we do this, we need to talk first about position, and in translational motion, position is represented by a point such as x. So in this diagram, we just have a line, a number line, basic number line, and we are at x equals 3. If I have rotational motion, position is now represented by an angle and by a radius. If we look at this picture, we have our angle theta and we also have our radius r. Notice that we're not going to use degrees anymore. We're going to go back to radians. So you want to make sure that your calculator is set back on RAD. You don't have to worry about looking at angles anymore necessarily. Depends on kind of what you're doing, but that tends to be the way it is. 90 degrees here is really pi over 2, pi for 180, and what we've been doing for 270 is 3 pi over 2. Notice that we're starting with our 0 over here, just as you would in math. If we look at the next one, we'll see that the displacement, or the change in distance, is typically represented by the vector delta x. So it has a magnitude and a direction. And for this one, the direction would be to the left or to the left side of the number line, and we do have a displacement of -4. Angular displacement is represented by delta theta, which is the angle. That's not a vector, so you have to be very careful. But it does behave more like one for small values, so we'll typically see these things happen in small values. The right-hand rule, which we'll do in a second, does determine the direction of that angular displacement. If we go on and look at tangential and angular displacement, when a particle rotates through an angle, for example, we have this angle here through a distance s, and so this would be part of the curve, and that's just the length of the arc defining the path. We can say that the distance s is related to the angular displacement delta theta, which is our angle change, by the equation the radius times that change in angle. And so you'll see that on this diagram. The instantaneous velocity, so how fast something is moving at an instant, is just ds over dt, and that's tangent to the circle. So we've got a couple different VTs here, which are instantaneous velocities. The same particle rotates with an angular velocity. Angular velocity, we use the Greek symbol omega, and that's basically just the change in the angle divided by the change in time. The direction of the angular velocity is always given by the right-hand rule, and the speeds are equated by the equation v is equal to r times omega. This is because omega, remember, really is just the change in position, or change in the angle, and that's a scalar. So if we multiply it times r, we're going to end up with a tangential and angular speed. So here's our angular speed, and that's our equation. Um, the kind of strange thing about this, we're so used to saying that the speed here is tangential, but for angular speed, we're going to say it's outward, so it's coming out towards us. Now, how do you do that? You're going to use the right-hand rule just like you did in magnetism. Simplest thing to do is curve your hand in the direction of the motion, and then your thumb indicates the direction of the angular speed. So my thumb is pointing towards me. Notice that this one was going counterclockwise, so that always comes out towards you. If it's going clockwise and speeding up, it would go into the page. So it's very similar to what we've been doing, just really easy right-hand rule, no big deal at all. Uh, Once again, just remember that the angular speed here is out of the page. That's positive z if we said that the z-axis was coming towards us here. To the right would be x, up and down would be y. So coming into and out of the page is the other. The acceleration that is tangential is given to us by the change in the speed divided by the change in time. And this acceleration is either parallel, so going in the same direction, or antiparallel, going in the opposite direction to the velocity. Angular acceleration is given by the equation alpha, that's angular acceleration, is equal to the change in the angular speed divided by the change in time. It's either parallel or antiparallel, we've already said that, and tangential and angular accelerations are related by the equation A. So here's our acceleration is equal to, there's r, which is our radius, times the angular acceleration. So if you know angular acceleration, if you multiply it times r, you'll come out with that overall acceleration. Don't forget about centripetal acceleration. Remember that has its own equation, and the equation is the centripetal acceleration is equal to v squared over r. Um, and so that would be pointing into the page. And that's just about it for that part. I'm going to get rid of this, go ahead and delete everything that is on the slide, then we'll move on. They want to know what is the direction of the instantaneous velocity here. So remember that this should be a just basically you go through and you draw a tangent line, and so this would be the instantaneous velocity, vt. What's the direction of the angular velocity? Because it's curving in this fashion, we say that it's coming towards you, so we'll just do our typical symbol. What's the direction of the tangential acceleration? So tangential acceleration would be going in the same direction. What is the direction of the angular acceleration? And once again, it's the same direction as the speed because it's speeding up. The centripetal acceleration would be AC, and that's pointing towards the center of the circle. And the overall acceleration of the particle, we'll talk about a little bit later. It's not real difficult, but for right now, we just don't need it. And so we're going to get rid of all the ink on the slide here. If the particle is slowing down, then your right-hand rule, you can make it the same way, but then it goes in the opposite direction. So if this was slowing down in this direction, it's really speeding up in the opposite, which means that instead of coming out towards us, that both the speed and the angular acceleration would be going into the page. So if it's going this way but slowing, it's just like when we thought about a electron. You had to use the left hand, or you just did the opposite of the right hand rule. So that's really not too awfully bad either. Just kind of learning as we go. Next page, the first kinematic equation that we have here, if you remember, is v is equal to vo plus at. You can substitute in the angular velocity for velocity and the angular acceleration for acceleration. So you end up with the angular velocity is equal to the angular velocity original plus the angular acceleration times your time. So that's really not bad. Second kinematic equation, usually we use this when we drop something if it doesn't have any initial speed. And now we can substitute all the angular parts in. And notice that now the angle is our position. Here is our angular speed times time plus 1/2 times the angular acceleration times time squared. So same equation, just different things that you're using because it's rotating. Third kinematic equation, v squared is equal to vo squared plus 2a times the change in position. We're going to substitute everything in again, and there we go. Just not a lot of difference between those. So let's go ahead and do a problem. In this problem, the Beatles' White Album is spinning at 33 1/3 RPM. So this is kind of a question that might be a little bit hard to think about because we don't even hardly use CDs anymore. But in old record players, you could see them go around. They'd spin at 33 1/3 revolutions per minute. For this one, it takes 1/2 minute for the album's rotation to stop. What is the angular acceleration of the phonograph album? So here we're going to say the angular speed is equal to the original angular speed plus alpha, which is angular acceleration times time. And at this point, we need to figure out what is alpha, and alpha here will be equal to the angular speed minus the original angular speed, all divided by time. And because we don't have, since this becomes 0, our equation really is just negative omega original divided by time, and that's because it stops. So at this point, we need to think about revolutions per minute. We really want to turn revolutions into radians. So to do that, we're just going to take that and multiply times 2 pi. And then because we have minutes here, we really want that in seconds, so we need to divide by 60 seconds. So here's kind of how this equation goes. We're going to put in our 33.3 revolutions per minute, and then to convert it to radians, we're going to do 2 pi radians in a revolution. So that should be over here. We're just going to put that in a revolution. And then 1 minute on top is our 60 seconds. And then on the bottom of this, we're going to have 60 seconds. And we know that we are looking at 1/2 of a minute to stop. So that's actually our time, which is 30 seconds. At this point, you're going to end up with 0.116 radians per second squared, and that's our unit of acceleration. So that one's really not too bad, pretty easy to do, pretty easy to see. So you shouldn't have any trouble with it. At this point, I think what we're going to do is we'll be done with this section.